Welcome to another related rates example. So in this example, a police car is driving toward an intersection at 45 miles per hour. And they see another car go speeding past on the cross street. So I have a diagram drawn below. The policeman pulls out their radar gun, which says the car is moving away from the police car at 15 miles per hour. If the police car and the speeding car are both a half mile from the intersection at the time of the reading, how fast is the speeding car actually moving? So here we have our little diagram, right? So the police car is going at a constant 45 miles per hour towards the intersection. The speeding car is heading away from the intersection. We're trying to figure out how fast it's moving away. And then the way the radar gun reads is going to be how fast this distance is changing. So I'm going to actually put the arrow over here. So the radar gun is seeing how fast is the distance between these two cars changing, the direct distance, not by the roads. So in this case, the diagram's already drawn for us. Again, if you want, you're welcome to kind of skip the words. I'm going to label my variables this time since there's not an obvious volume and radius variable. So I'm going to label the police car distance from the intersection as P. So if we set P equal to the police car's distance from the intersection. Then that 45 miles per hour, that's telling us that the rate of change of this variable, so dp dt, is equal to negative 45, and then I'm just going to put miles per hour on the side. So again, this is P is that distance there. And then I'm going to go ahead and label the speeding car's distance from the intersection as S. So we'll make this distance S from here to the speeding car. P is from the intersection to the police car. So we'll set S equal to the speeding car's distance from the intersection. And then we'll set, I'm going to just use R for radar gun. So this distance will be R. So R is the distance between the police car and the speeding car. And then what we have, I should have put for these other ones. So the speeding car, so ds dt would be the speeding car's speed away from the intersection, right? And then dr dt will be the radar gun, what the radar gun would read. So this would be the speed read by the radar gun. So in this problem, what we know is that the police car's speed, dPdt, is negative 45 miles per hour. Again, velocity, technically, the rate of change includes direction. So since that distance is shrinking, it's negative. Then we want to know, or we know that the rate of change read by the radar gun, dRdt, was equal to the radar gun read 15 miles per hour when both cars were a half mile from the intersection. So dRdt equals 15 miles per hour when the police car's distance is 1/2 and the speeding car's distance is 1/2. And then we want to know ds dt, the speed of the car, when p equals 1/2. Oops. And s equals 1/2. So I'm not labeling the steps anymore. I'm just kind of writing out all the information from the problem, labeling things so I know what the variables are referring to. This is all kind of understanding the problem and translating it into math. And so this was kind of those first 2 steps. From here, we now need our formula. So write down the formula or the equation to relate. In this case, the variables involved are P, S, and R. So again, if we kind of zero in on what we were focusing on, we have a right triangle with P, S, and R. Okay. And these are the distance or the length of the sides and the hypotenuse. So we can use the Pythagorean theorem which tells us that p squared plus s squared should be equal to r squared. Once we have that, we can go ahead and differentiate with respect to time. And so we have ddt of p squared is equal to, oops, sorry, ddt of p squared plus, let's do all this in one go. So ddt of p squared plus s squared is ddt of r squared. And so we wind up with, if we differentiate p squared with respect to t, we will have 2p times dp dt. Then we would have plus 2s times ds dt. And this is equal to 2r times dr dt. If you wanted, we could simplify. So I'm going to just go ahead and divide both sides by 2. And we wind up with p times dp dt plus s times ds dt is equal to r times dr dt. Once we have that, we can go ahead and plug in. So again, the information we have, we know that dp/dt is -45 miles per hour. We know that P is equal to 1/2 miles. S is equal to 1/2 mile. And dr/dt is equal to 15 miles per hour. We can find R using these two pieces of information here. So we would have that R would be equal to the square root of P squared plus S squared. So 1/2 squared plus 1/2 squared. And we get that R is equal to the square root. 1/4 plus 1/4 is 1/2. So if we take our original equation and plug all of this in, we have P times dp/dt plus S times ds dt is equal to R times dr dt. So we have 1/2 times -45 plus 1/2 times ds dt is equal to the square root of 1/2 times dr dt is 15. So from here, we're just solving for ds dt. So we have -45/2. We could go ahead and add to both sides. Sorry, plus 45/2 to both sides. And we would have 1/2 times ds dt is equal to 45/2 plus 15 times the square root of 1/2. And if we just multiply both sides by 2, we wind up with ds dt is equal to 45 plus 30 times the square root of 1/2. And if we go ahead and plug that into a calculator, we wind up getting this is approximately 66.2. Again, S was in miles, T is in hour, so this would be miles per hour. So again, if we just put this back in context, the speeding car is traveling or was traveling at about 66.2 miles per hour at the point of the radar gun reading. So again, this is a little more complicated for figuring out how fast a car is going if the cars are kind of moving perpendicular to each other, not in a line. So as your textbook mentions, your textbook does a similar problem. As your textbook mentions, there's a reason why police cars typically are just pulled off on the side of the road, so they can just watch the car go by instead of having to do calculations.